In the previous video, we had 4 participants and any 3 of them could recover the secret. And so that was a 3-4 threshold scheme. And in general, we write this as a Tn threshold scheme. So here n is the total number of participants and the number t is the threshold. And so this is the minimum number of participants needed to recover the secret. So now the secret for our purposes is going to be an element of ZP, where P is going to be a prime number for us. So P prime, and we'll discuss why later. So we're going to want to work over ZP. And we also need to assume that the number of participants is going to be less than P, or in other words, that you need to choose this P to be larger than the number of participants. The reason for that, we saw that you need to send evaluation points, and since each participant receives a different evaluation point, you need to have enough evaluation points. So this set needs to be large enough for each participant to get something, and they can't get the evaluation at 0 because that's where you put the secret. So that's why you need the n smaller than P. And so the construction has 3 steps, and it just follows what we said before. So you choose t-1 keys, right? Because so the keys are what we call these random numbers here. So we choose t-1 keys r1 to rt-1 uniformly at random from ZP. Then we define the polynomial f of x equal to the secret plus, and then you use the randoms as the coefficients that appear in front of these monomials up to x to the t-1. So of course, we want to do it up to x to the t-1 because, like we said, any polynomial of degree t-1 can be determined by having t evaluations. So that's why you do things over a polynomial of degree t-1. And then to each participant, you need to send an evaluation of this polynomial, where so alpha I is going to be some evaluation that participant I receives, and these need to be distinct. You can't send the same evaluation to different participants. And they need to be different than 0, because if you send the 0, you're sending the secret, right? And so this is the reason that you need the P to be larger than n. And so before we go further, let's talk about Zn again. Why are we talking about Zn? What's going on here? So what is Zn again, right? What is it? So Zn, if you recall, was this set with the numbers from 0 to n-1, where we used the clock arithmetic, right? So we put the numbers in a clock. We start at 0 and we go, let's say, clockwise here, and we put the numbers here. And then addition and multiplication is done in the clock, just going around, right? And so it's equivalent to doing addition modulo n. And one of the things that we saw before is that when are we able to compute inverses in Zn? So when is it that if we have an element in Zn, A, that we also have, so when does a to the -1 exist? And we saw that this happens when the GCD between A and N is 1, so that means when they are coprime. Now, if you choose a number n to be prime, so if n is prime, then every element, so every A in Zn, every element here is going to be coprime with n because n is prime. And so every element will have an inverse. And that is what we call, so this set Zn with addition and multiplication and all its properties and everyone having an inverse, it's what's called the field, which we have slides on this in a previous lecture. But for now, the important thing that matters here is that we want to work in a field because we want to be able to solve linear systems. And to solve linear systems, we need to be able to invert stuff. And so that's sort of the reason why we do everything over ZP, where P is prime, right? And so why work over the finite field ZP? So like we said, we need to solve linear systems. To be able to do that, we need to add, subtract, multiply, and divide by non-zero elements. And so we need to have that every non-zero element has an inverse. And this is what's called a field. Like I said, we have this in a previous lecture in the slides. So this is what's called a field. And so that's the reason that we work in ZP. Now, the reason that we need to work, because one could, so the real numbers are also a field. So is also field, right? And also like the integers, also a field. But the issue with that is, so for example, over the integers, why not just do everything over the integers, right? The issue is that one of the things that we do is that we choose things uniformly at random, and there is no uniform distribution over the integers, because think of it like this. If there was a uniform distribution over the integers, then every number would have to have the same probability of occurring, and it would have to be like some number. But if you sum over all of them, you would have to have one, but you have an infinite amount, so you can't have that happening. So there's no way to choose uniformly from Z, and so that's one of the reasons that it's good to work over something finite. And since we want to do linear algebra, finite fields. And so that's the reason we work over ZP with P prime.